All right, let's start talking about rotational kinematics. Um, so basically, what you're going to find with the rotational motion is we're going to hit a lot of the same beats that we hit with linear motion, just from a rotational point of view. So the first thing we're going to hit is rotational kinematics. The second thing we'll hit is torque, which is kind of the rotational analog to forces and dynamics. And then we'll take a look at rotational momentum. Um, Now, anytime we're talking about rotational motion, what we're talking about is the objects of motions that spin about some sort of fixed axis. So a good example would be a fan or a merry-go-round or a wheel. So anything that is spinning around some center of rotation. Now, with linear kinematics, what we cared about was displacement in meters, right? X. But when we're talking about rotational kinematics, we don't care about some linear distance. Rather, we care about um, the amount of angle that the object sweeps through. So theta is going to represent the angular displacement of the particle. Um, and now theta is going to be measured in radians. So make sure that you are at least a little bit familiar with the unit circle. Um, at least in terms of this being 0, pi over 2, pi, 3 pi over 2, and then 2 pi. That's pretty much all you probably need, but it is helpful to have that understanding of the unit circle. Um, Now, when we're talking about position, obviously position can be positive or negative, just like it was in linear kinematics. Now, the direction that is positive is going to be counterclockwise, right? Whereas clockwise is going to be negative. And the reason that counterclockwise is positive is because, well, that's the direction you go through the unit circle. Now, one other thing to keep in mind is that when we're looking at radians, keep in mind that one revolution is equal to 2 pi radians, and you'll often need that conversion ratio. Now, as something moves in a circular path, so say from here to here, right, it does cover some arc length that we're going to call S. Now, we can determine that arc length that the object travels based off of looking at the angle that it sweeps through and how far away it is from the center of rotation. So for instance, if we're looking at a dime and a penny on the CD, right, as it spins around the center of rotation right here, the center of the CD, if we were to rotate this pi over 2 radians, they've both undergone the same angular displacement. But the penny has traveled a greater arc length than the dime has. Right? So it's all based off the distance from the center of rotation. So no matter where you place these objects on this fixed rotating surface, the angular displacement will be identical, but the arc length that they travel will vary based off of where along the disk that they are located. And so just like when we were looking at linear kinematics, if you were looking at velocity being a change in linear position over a change in time, well, your angular velocity, which is going to be represented by the Greek letter omega, is going to be equal to a change in angular position over a change in time. So this would be the equation for something moving with constant angular velocity. So if we look at example 7.1 in the notes, we want to find the angular velocities of the two particles in this figure here. Well, let's start with the one on the left. In 5 seconds, it covers 90 degrees, right, which in radians is pi over 2 radians, and that occurs in a time of 5 seconds. So your angular velocity would be your change in angular position over time, right, which would be pi over 2 radians over 5 seconds. So that'd be pi over 10. So 0.314 radians per second. And again, notice the units there for your angular velocity. It is radians per second. Just like in linear velocity, you're dealing with meters per second. Now, in the right picture, we have 180 degrees covered. Right? So, theta, in this case, is pi radians over a time of 5 seconds. So omega is a change in angular position over time. So pi radians over 5 seconds. So we do the math there. And we get 0.628 radians per second. Alright, so again, it's not really anything new. It's just dealing with things from a rotational point of view rather than a linear point of view. So let's take a look at the next example. In this one, we've got a roulette table. We got a small steel ball. It rolls counterclockwise. So it's rolling counterclockwise, which means that your angular velocity is going to be positive. Inside of a 30 centimeter diameter roulette wheel, the ball completes exactly 2 revolutions in 1.2 seconds. We want to know the ball's angular velocity and the ball's angular position at time equals 2 seconds, assuming that it starts at an initial angular position of 0. So let's go ahead and start just listing out what we got. Now we know the radius of this wheel is 15 centimeters, so 0.15 meters. We know it completes 2 revolutions in a time period of 1.2 seconds. Now that 2 revolutions is going to be our angular displacement, but keep in mind that we cannot be working in revolutions, we have to be working in radians. So let's go ahead and convert that to where 1 revolution is 2 pi radians. So we have an angular displacement of 4 pi radians. So if we want the ball's angular velocity, right, it's a change in angular position over time. So 4 pi radians over 1.2 seconds, and we get an angular velocity of 10.5 radians per second. Now the second thing we want to know is what is the ball's angular position at time equals 2? Well, if this is a constant angular velocity that we just found, again, we look at our equation for a constant angular velocity where it's change in angular position over time. And we have 10.5 radians per second is equal to our unknown position over 2 seconds. So your angular position is 21 radians. And again, that's because we can assume that your initial angular position is 0. So remember, when you're looking at delta, that means change. So final minus initial. And if initial is 0, your change in angular position is going to be your final angular position. Now, just like with our other units, period and frequency come up. Period and frequency are defined the same in this unit as the last. Right, the period is the amount of time it takes to complete one full cycle, and the frequency is how many cycles it completes per second. So let's take a look at example 7.3 together. Now in example 7.3, we have the crankshaft in your car engine is turning at 3,000 RPM, so revolutions per minute. What is the shaft's angular speed? Now, this equation up here in the notes, this omega equals 2 pi radians times frequency, you can kind of ignore this because you can get your angular speed based solely off of dimensional analysis. So what do we mean by that? If your car is rotating at 3,000 revolutions per minute, well, we know that one revolution is 2 pi radians. We know that there is 60 seconds per minute. Well, look at your units here. Revolutions cancel, minutes cancel. So whatever you're solving out for in this dimensional analysis is measured in radians per second. So what are we actually being given here? We're being given the angular speed. So you can get your angular speed from the revolutions per minute just by doing basic dimensional analysis. So 3,000 times 2 pi divided by 60, which gives us 314.2 radians per second. Alright, so the key here is understanding that whenever you're given something in RPM, what you're being given is that angular speed, and you just got to do a little dA to get it to radians per second rather than revolutions per minute. Now, keep in mind, just like when we were looking at the arc length traveled by an object being based off of how far it is away from the center of rotation, it's going to be the same thing for the linear speed. So if we're looking at the linear speed of an object on a rotating disk, it's going to depend on the angular velocity and how far away it is from the center of rotation. So if we bring that CD back up, well, if we rotate this CD again 90 degrees, both the penny and the dime covered the same angular displacement in the same amount of time, right? So they would have the same angular velocity. But one of these covered a greater arc length. So the penny covered a greater arc length over an equal amount of time, so its linear velocity is going to be greater. Right, so the distance from the center of rotation is going to determine what the linear speed, the tangential speed of the object is. Right, so both the dime and the penny have the same angular velocity, but they have different linear or tangential velocities based off of how far away they are from the center of rotation. So in example 7.5 in the notes, we have a CD player, and the compact disc is 12 centimeters in diameter, and the disc is spinning at its maximum rate of 540 revolutions per minute. We want to know the speed of a point at a distance of 3 centimeters from the center, and one that is at the outside edge of the disc, 6 centimeters from the center. Alright, so first things first, let's get that RPM into radians per second. So revolutions per minute. Again, one revolution is 2 pi radians. There's 1 minute per 60 seconds. And so we get a angular velocity of 56.5 radians per second. So in A, we want to know the tangential or linear speed of something at 3 centimeters from the center of rotation. So V equals omega R. So V equals 56.5 radians per second times our radial distance of 0.03 meters. And so we get a linear speed of 1.7 meters per second. Now in B, we're looking at a spot twice as far, so 0.06 meters. So V is equal to omega r. So V equals 56.5 radians per second times 0.06 meters. So V in this case comes out to 3.4 meters per second. And again, the reason this one has a greater linear speed is because it's covering a greater arc length in the same amount of time. So take a minute, look at Stop to Think 7.1, which particle has the angular position of 5 pi over 2. Pause the video, see if you can reason that out. Alright, easiest way to determine this is if we know that 90 degrees is pi over 2, well, just look at this. 1 pi over 2, 2, 3, 4, 5. Your answer has got to be A. Alright, so again, just know the basics of the unit circle. 90 degrees, 180, and so on. Because if you know those, it's going to make your life a lot easier, right? So pi over 2, pi, 3 pi over 2, 2 pi. Alright, so the last thing we want to look at is angular acceleration. And when we are looking at angular acceleration is going to be represented by the Greek letter alpha. And it is a change in angular position over a change in time. Right, just like our linear acceleration was a change in velocity over a change in time. So we look at our units here, radians per second. So alpha is going to be measured in radians per second squared. So really, there's a ton in common, right, between your rotational kinematics and your linear kinematics, so you should feel fairly comfortable with at least this portion of rotational motion. Now, just like with linear kinematics, if we have angular acceleration, we can derive 3 kinematic equations. Now, these should look really familiar to you. Our final angular velocity equals our initial angular velocity plus angular acceleration times time. Omega squared equals omega naught squared plus 2 alpha times theta. And theta equals omega naught t plus 1/2 alpha t squared. Right, these are identical to the linear kinematic equations. Right, just instead of v, we're replacing it with omega. Instead of acceleration, linear acceleration, we're replacing it with angular acceleration alpha. Instead of distance x, we're replacing it with theta, the angular displacement. Right, so if you look at our linear counterparts, right, these are not new equations. We're just replacing the linear variables with the rotational ones. So in example 7.6, we're spinning up a computer disk from rest to a final angular speed of 5,400 RPM in 2 seconds. We want to know what the angular acceleration of the disk is, and at the end of 2 seconds, how many revolutions has the disk made. Alright, so we know that our initial angular velocity is 0 radians per second. Right, it starts at rest. Our final is 5,400 revolutions per minute. And again, 1 revolution is 2 pi radians. 1 minute has 60 seconds. Which gives us 565 radians per second. And so we want to know what is our angular acceleration. Well, again, you just scan through your equations, right, just like we did at the beginning of the year. Right, and we've got enough information to use that first equation, where 565.5 radians per second is equal to 0 plus unknown angular acceleration times a time of 2 seconds. So our angular acceleration in this case comes out to 282.7 radians per second squared. Now, we also want to know what its angular displacement is. Now, we could use either one of these two equations. I'm going to use this one just because omega naught is 0, so that whole term goes away. So theta is equal to omega naught t plus 1/2 alpha t squared. If omega naught is 0, then your angular displacement equals 1/2 of your angular acceleration times time squared. So theta equals 1/2 of 282.7 times 2 seconds squared. So theta comes out to 565.5 radians. Now, if they're asking for how many revolutions this disk completed, all you've got to do is convert the radians to revolutions. So 565.5 radians. And there are 2 pi radians in every revolution, which gives us 90 revolutions. Now, just like our arc length depended on the angular displacement and the radial distance, and our linear velocity depended on our angular velocity and the distance, well, our tangential acceleration is going to depend on the angular acceleration and the distance. So the further away you are from the center of rotation, the further you travel, the faster you travel, linear speaking, and the greater your tangential or your linear acceleration is. Now, keep in mind, when we're dealing with rotational motion, you have the possibility that you have 3 different accelerations running around. If the object is changing direction, meaning that you've got something, say, again, like a coin on a disc, right, that's just rotating. Well, that coin is moving in a circle, right? So it has centripetal acceleration. So it's possible to have centripetal acceleration. Now, if this disk is speeding up, well, it's got angular acceleration. And if this disk is speeding up, well, this coin, its linear velocity is also speeding up, which means that it has tangential acceleration. So it's possible to have 3 different accelerations running around out there, so you want to be careful when, especially you're dealing with concept questions, that you're being very specific in terms of the language you're using, right? Are you talking about centripetal acceleration, meaning that the coin is changing directions? Are you talking about angular acceleration, meaning that the angular velocity is increasing? Are you talking about tangential acceleration, meaning that the linear speed is increasing? So you want to be very careful about the language you use when we get to acceleration. So lastly, let's take a look at Stop to Think 7.2. So in 7.2, we have a ball on the end of a string, and it swings in a horizontal circle once every second. We want to state whether the magnitude of each of the following quantities is 0, constant, but not 0, or changing. So pause the video, look at those options, and think about what's going on with the magnitude of each of these variables. Alright, so this ball swings around once every second, which means that it is in a state of uniform circular motion. So if we look at the velocity is changing. Now the reason the velocity is changing is because the direction is changing. Now if A had just said speed, then speed would be constant. But again, they use the term velocity, which includes speed and direction, and because direction is changing based off of moving in a circle, velocity is by definition changing. Now B, your angular velocity, that would be constant, because again, you're sweeping through the same amount of area per unit time. You're sweeping through 2 pi radians every single second. C, your centripetal acceleration, that would be constant, right? Because your linear speed doesn't change, and the radius of the rotation of the ball doesn't change. D, angular acceleration. Angular acceleration would be 0 because the angular velocity is constant. And E, tangential acceleration, that would be 0 because the linear velocity of the object is constant. So the answers again would be changing, constant, constant, 0, 0. Now the next thing we'll be covering will be torque, but that won't be towards the end of the week. I will be uploading some basic rotational kinematic problems here, probably tomorrow. But yeah, if you have any questions, you know where to find me.